Okay, here is some examples, or here are some examples to support day 3. These are examples in chapter 20, 20.10. It's in the textbook if you want to actually read the example. Here it is written out, plus you have this worksheet, and I'll just go through with you how you would solve this. A voltaic cell is set up with an aluminum electrode in a 0.025 molar aluminum nitrate solution, and then an iron electrode in a 0.5 molar iron nitrate solution. Calculate the voltage produced by this cell. First of all, we'll draw the cell diagram. You just go ahead and put in the molar amounts of the solutions. It's the metal ion that we're interested in, aqueous. We're not interested in the nitrate. And then this line represents the division, or the division between the solution of aluminum ions and the aluminum metal electrode. This double line here represents the salt bridge, or whatever dividing material there is between the two electrodes in the cell. Then over here on the other side is the iron, the solid metal piece of iron electrode. And again, another single line, 0.50 molar iron ions that are in solution. And you don't really know yet which one's oxidation, which one's reduction. That doesn't really matter, but just notice that you've got the aluminum and the iron, and then in the aluminum ion solution and in the iron ion solution. So that's just a little, that's the typical way cells are written on paper to kind of visualize everything that's happening. Now, if this were happening at standard conditions, meaning at 298 Kelvin, which is 25 degrees Celsius, and the solutions were at 1 molar, both of them, then the calculation would be pretty fast and quick. And we're actually going to do the calculation that would be pretty fast and quick too. We just can't stop because it is not at standard conditions. Alright, so cath is just my abbreviation for cathode, and E at the anode. What we don't know yet is which one is the cathode and which one is the anode. And the way we figure that out is that we take Appendix M, which is essentially some version of the standard reduction potentials. And the way these are always written is they're all as reductions. In every single case, every single half reaction that you see, the charge is going down. It doesn't work that way, of course. Every redox reaction has a reduction and it has an oxidation. So the way it works is you look for the two half reactions that could be occurring, and the two that could potentially be occurring here in this reaction are the aluminum and the iron. So our aluminum is here. There's our aluminum, 3 plus 3 electrons forming solid aluminum. And then our iron, 2 plus 2 electrons forming solid iron. Iron is above it. It's a table of reductions with the highest value up here. So whichever one is on top, the way I think of it is it gets to be the reduction, and then the one that is below for the particular reaction is forced to be the oxidation for at least this particular question. So aluminum may at another time in another redox reaction actually undergo reduction if it were in a reaction with something below it. But for this instance it's not. Aluminum is the loser, if you will. It's going to undergo oxidation, and iron is going to undergo reduction because it's just literally on top of it, or has a less negative standard voltage. So we now know which one's our cathode and which one is our anode. So we write down the cathode value. That's the reduction. That's the one for iron. So again, make sure this matches up with what you saw on the chart.
Is that okay?
Okay.
Oh yeah, just come in.
Negative.
Thank you.
This just came straight off of our table of reductions. I'll just pull that back briefly so you can see it. There it is. Took it exactly as is. And then you write subtraction and you use the anode value. you use it, again, the anode value underneath, you use it straight off the table. It's negative 1.66. Then we're going to write negative 1.66. You don't change the sign or anything. The reaction, or the equation has, the minus sign kind of takes care of that for you, if you will. So you don't worry about changing the sign. And of course, minus a negative means positive. So the value comes out to be positive 1.22 volts. That's our standard potential. Again, this is at standard conditions. What are standard conditions again? It means 298 Kelvin and 1 molar solutions. The temperature is not discussed in the problem. If there's no temperature given, you can assume that the temperature is standard or 298, but the molar quantities are not 1. So it's very clear we are not at standard conditions. So therefore, we're not done. If we were at standard conditions, we would be done. It's literally just a simple subtraction of the reaction that's taking place at the cathode, which is the reduction, minus the reaction taking place at the anode, which is the oxidation. I'll just put that in here in the notes for a reminder of that. That's where our oxidation takes place, and the cathode is where our reduction takes place. And then we have the Nernst equation to lead us to the actual cell voltage. So E cell, notice the little degree symbol is gone there because we're not at standard conditions anymore. Standard conditions, we just calculated it up here. We're going to use that value soon. Minus volts per 6 moles of electrons. I'll get to in a minute where that 6 came from. We need to go through that. You don't know yet that it's 6, and I'll show you where it came from. And then log of Q, which we need to get also. The Q value is going to turn out to be 0.005, but I will show you how to get that also. So in other words, the E cell we got, the standard we got by simply subtracting. The 6 moles of electrons we're going to get by balancing the 2 half reactions. Pretty quick and easy to do now that you've balanced equations. It won't take that long. And Q, we've calculated those before also. Or there's 3 pieces of the puzzle that we need. We need the standard voltage, we need the number of electrons that are actually, or the number of moles of electrons that are actually transferred, and we need our reaction quotient. So, the first thing we will do is show you, or what I'll do is show you where the 6 moles of electrons come from. Where did that arise? Well, we decided that iron undergoing reduction, iron 2+ undergoing reduction to solid iron was our reduction, and then our oxidation had to be aluminum, so we turned the aluminum reaction backwards from what's on Appendix M. And it looks like this. As you notice, there's 2 electrons here, there's 3 electrons here. We have to balance that. We're going to multiply this whole reaction by 3, this whole reaction by 2, with the whole purpose simply being how many electrons are transferred. So the overall equation becomes 3 iron ions, or 3 moles of iron ions, plus 2 moles of aluminum metal, plus 6 moles of electrons, yields 3 moles of iron, moles of aluminum ions, plus 6 moles of electrons. The 6 electrons, they actually technically leave. They're the same on both sides of the equation, so we take them out. But that's where our 6 moles came from. It took 6 moles of electrons to reduce the iron and oxidize the aluminum because of the 2 half reactions that they came from. So that's where our 6 moles came from. Q. Q is our reaction quotient. It's calculated just like K is. And here again is our reaction that we're going to use for that. Remember, K values and Q's, we don't use the solids, we only use the aqueous solution, so that simplifies it quite a bit. We take our concentration of our aluminum ion, square it because of the 2 coefficient, concentration of our iron ion, and cube it because of the 3 coefficient in the reaction, and then fill in the concentrations that were provided in the original problem. So this one squared, this one cubed, and mathematically you plunk that into your calculator, or possibly the numbers might be easy enough you can calculate it by hand, and you're going to come up with 0050 as your Q value. And that's where that will go. So putting it all together, just so you can visualize it, the E for the cell at these non-standard conditions is equal to that standard value we calculated first thing at the top, minus this combo value that we got off the reference packet. Times the natural log of Q. Please practice with your calculator. Make sure you can actually mathematically get all of this done. And if you do it correctly, it should come out to 1.24 volts, or just a teeny little bit higher than under standard conditions. Standard conditions, it would have been 1.22 volts per mole of electrons, and here it is 1.24. So that's example 2010. If you flip over to the other side of your paper, here's a question. This is example 2011. The following reaction has a standard cell value of negative 76 volts. First of all, and then here's the net equation provided to you. And the question is, calculate delta G for this reaction. Is the reaction product or reactant favored? Right off the bat, without doing any math whatsoever, you already know that it's reactant favored without doing a thing. And the reason for that is because the voltage is negative. When you calculate the voltage and it comes out negative, that means it will produce that electric current spontaneously on its own without trying. Or it's a battery, it can provide that much voltage. Calculate the delta G. This is from the PowerPoint. There is an equation that will provide for us a delta G from a standard, or vice versa. If you have a delta G at standard conditions, it'll give you the voltage, or if you have a voltage, you can get the delta G. You can even calculate the number of moles if you had both of those, etc. Like any other equation, you can find any of those. And then fill in your values, delta G, standard conditions, minus 2 moles of electrons. Why 2 moles? Because if you look back up here at the balanced equation, it's going to take 2 moles to go from zinc 2+ to zinc solid. It's going to require 2 moles of electrons. Faraday constant, 96,500 joules per volt times mole. And then the voltage provided in the problem, negative 76 volts. And so our delta G value comes out to 150 kilojoules. as should have been anticipated, delta G is positive. Oops, and I said something backwards. I said that amount of voltage would be produced. No, it wouldn't. That would be the amount of voltage required. In other words, this is not spontaneous. It is reactant favored, and then delta G is positive because all of those things go together. That requires this much energy. Electricity, in order to have it happen, it's not spontaneous. That means it's reactant favored, positive delta G. All of those go together. Last example. Calculate the equilibrium constant for this reaction. So the net ionic equation is provided to you. And to calculate the equilibrium constant, you're going to start by dividing this into the oxidation and the reduction. The oxidation is mercury, liquid mercury becoming mercury ions, 2 electrons, 2 silver ions undergoing reduction to 2 moles of silver. All of these 2's are here because of the 2 electrons here. It's got to match. If there are 2 electrons involved in the reduction, if there are 2 electrons involved in the oxidation, there must be 2 involved in the reduction also, or vice versa. So, equilibrium constant, E for the cell is equal to, as always, the reduction value minus the oxidation. We know which is which. The reduction value, again, comes off of your appendix M, 0.7994 minus 0.855. If you do the subtraction, it comes out to minus 0.0556, and it's negative. That means it is not spontaneous. That means that you cannot use it as a battery. It's going to require that much electricity in order to make it happen. And that's not surprising because as it is written, the oxidation was on top of the reduction in Appendix M. So we now know, as we go ahead and calculate our equilibrium constant, log K is equal to 2, that's our number of moles of electrons, minus 2 times negative 0.0556 volts. And that's, oops, I'm a little bit too low. I'm going to slide this up so you can get a good look. Our K value is coming out to negative 4.3, or log K, I'm sorry. So K is equal to 0.013, or 1.3 times 10 to the negative 2. Or it's a small K value. It's not really small, but it is small, which again should match up with our voltage being negative, being not spontaneous. It's more reactant favored than it is product favored. All those things go together. And that ends the examples.
Stop.